Andy Schweitzer. I'm doing a quick little video here. This is our PowerPoint, our classroom PowerPoint on significant digits. One of the more, I think, logical concepts for significant digits. It's just purely mathematical, and this is what we do in class. You can come to class, or I suppose this is going to be basically the same thing, same PowerPoint. All right, so what is a significant digit, and why do we need to know about significant digits? Well, first of all, a number is only as good as a tool used to measure it, and keep that as an underlying concept that is extremely important. So we want to be aware of the accuracy of a number. So you can use the measurement PowerPoint or video and see where it says you measure what you know and you estimate one digit using some sort of measurement tool, and it's got some lines on it, and maybe you're measuring the length of a pencil, okay, and you'd use the tool to determine which numbers matter. Measure what you know, estimate one digit. But when you're doing calculations, the question is, when you multiply, you divide, what happens to the accuracy, and where do you cut off your number? Okay, and that ultimately is what this PowerPoint will allow us to do is when you have a calculator, okay, where do you cut your number off? It's 5.63791, okay. Where does this number just get chopped off legitimately? And it's based off the accuracy of your tool. If your tool can only measure this far, then taking that number and multiplying, dividing, whatever, should not allow you to gain accuracy, and therefore the number should always be cut off after the 10th place and whatnot. So again, the overall goal here is when we're measuring, where do we cut off a value? All right, so the term significant digit. One, it must have a value, okay, and that value must be known. That may sound strange. When would a number not have a value, or when would that value not be known? We'll see a couple of examples of that as we move through this PowerPoint. Okay. All right, so how long is this line? Okay, now you could use two tools, okay, for example, and the line is, let's just say hypothetically, 25.00. Now, I use this line here, and I commonly refer to this as the rounding line, okay. Now, the rounding line separates what you know from what you don't know. There's still numbers here, very valid numbers. Our tool just can't see them. A better tool might give a better answer, 25.0031. Yet these are still, and they go on until you get down to the level of the atom, apparently. But tool B is more accurate than tool A. So we have more significant digits. Again, like I said, it's measure what you know and then estimate one digit. The person who's using the tool here is following that rule to give me this number, which is why they cut off this. They didn't continue to add more numbers because the tool couldn't provide them. Okay. All right. So measured values, they always contain error. At some point, the tool runs out of accuracy, and therefore you have some error inherently. Could be small, but there's some sort of unknown there. A number is only as good as the tool used to measure it. So, for example, 25 meters, 25.00 meters is never exact. You can never have an exact 25.00000000. Eventually, your tool runs out, and the numbers beyond it you just don't know. All right. Question mark equals the number a tool couldn't measure. There's no infinite measurement tool. So measured values always contain some error. Now, an exact value, there would be no error. Usually it would be a whole number, okay? For example, how many smiley faces do I have here? There's 2 of them, and now there's 3. If someone asked you, okay, I'll bet you that there are $1,000 that there's 3 smiley faces here, you'd be like, okay, how much you want to bet? I'll bet as much money I have, because you are 100% positive. There is 0 error of 3 smiley faces here. Just like you have 5 people and 10 cows. It's a whole number item with essentially no error. You really didn't use a tool to count them. You visually inspected that there's 5 there. Okay? This is called an exact value. Distinct difference between a measured value. Again, an exact value is an infinite significant digits. 5 people, okay, you can have that, that's fine. 5.0000, sure, still good. 5 people could be estimated as, I mean, this line can continue on and on and on and on, and it still would be exact to 5 people. It's exact. So because your 0 continues on, your accuracy continues on forever, we call it an infinite significant digits for an exact value. And we use this thing right here to describe it. I got this off of Wikipedia as the name of this thing, but it means infinite. It's like a horizontal 8, tipped over 8, and it means infinite number of sig figs. Now, the decimal rule, okay, is a rule that you see different people provide different ways of dealing with a decimal. But in our class, if a number does not contain a decimal, then it is considered to be an exact number. But check units to verify. Okay? Keep in mind, if a number does not have a decimal, we will consider it to be an exact value. But again, not everyone follows this rule. So check units, and that is ultimately what's going to tell you whether it is going to be an exact value or whether it is going to be a measured value. And there might be some gray area as to whether it's measured or whether it's exact. For example, 25 cows. Now there's no decimal here, but is it 25 cows an exact value? I think so. I mean, this number could get bigger and bigger and bigger, and eventually you ask a farmer how many cows does he have, he might say, about 250. Does that mean exactly 250, or does it mean an estimation of 250? It could be exact or it might not. You might say, how many people live in the state of Wisconsin? About 5 million. Does that mean exactly 5 million? No, it's an estimation. So anything that's measured generally would be an estimation. So for another example here, 25 meters. Now there's no decimal point here, but a meter is never going to be an exact value. It's a distance measured with a tool. Therefore, we'll drop the decimal back in there. Exact value, measured value. The unit can very often tell you what's going on. Now, okay, so 2 things we need for something to be significant. You have to have a value and we have to know what it is. 1 through 9 are real simple. They are what they are. 1 is 1, 9 is 9. That's not changing. If you measure what you know and estimate 1 digit, 1 is 1, and 9 is 9, 5 is 5, it doesn't matter. Those are always significant. Any typical number is significant. Only time we tend to have issues is when we start dealing with zeros. Okay? And we classify them in various ways, but in the end, it does make logical sense as to what that 0 is doing. So the question is a 0 always meaning 0? Well, in this case, we have 50,000 people. Let's say at a Packer game I have here. Nowadays, the Packer Stadium holds much more, but years ago it was smaller. 50,000, does that mean actually 50,000 people? Could or could not. In this case, there could be just looking at the crowd, and you could be sitting in the crowd and estimating based on your visual tool of your brain, looking at the crowd and saying, I think there's about approximately 50,000 people here. Your accuracy might cut off right here, in which these numbers, there are actually numbers here, we just don't know what they are. The tool you're using cannot indicate those numbers. If you could, sitting at a Packer game, you'd be quite unusual. If you're sitting in a game and someone says there's 50,526 people, 5,500 and 200 and let's say 21 people in this thing, they're going to think you're a little strange. So in that case, they would think you're lying. I don't know. So sitting in your seat, this is an estimation of 50,000 people. So these numbers have a value. We just don't know what they are. So they are not significant. We only have one significant digit in this particular number. Okay. Now, the question is when does number become accurate? When does it become not so accurate? And when is it an estimate? When is it used as a measurement? And there's my rounding line. I plopped that on there. So is there a difference between 2,000 and 2,000 decimal? Okay, this is how we will deal with it in this class. 2,000 could be an estimate of, whereas 2,000.0 is not. How far is it from, across the Hortonville School District? Let's say 2,000 yards. Or if you told someone that, you would think, about 2,000 yards. You would assume that this person is at some point estimating, and I'm going to cut it off right here as being one significant digit. Only one that's really actually known. But if someone says, okay, what's the difference across the Hortonville School District, and you say 2,000.0 yards, by adding that 0.0, you're exposing the level of accuracy that you are using. Regardless of the tool, you're exposing its accuracy. In this case, because the tool's accuracy ends here as opposed to right here, we have one significant here, and we have 5 significant digits here. But once you go past the decimal, you're showing accuracy. That 0 did not have to be there, yet you added it because of the tool you used. Over here, these zeros have to be here, and we will be pessimistic in this case and say, if zeros go up to a decimal but don't cross it, we're going to treat this as an estimate. Okay, 1 sig fig. Now, once it crosses that, there we go. It becomes an actual. All of them become significant. This has 1, 2, 3, 4, 5 significant digits. The tool measures here. Everything beyond here, we don't know. This side, we do. Same thing here. It ends here. This side is good. This side, not so good. Leading zeros. Okay, leading zeros are not significant. This simply placeholders showing where the decimal point is, and they don't exist yet. There's no number there. We know that there's nothing there. The number just hasn't started yet. This has 2 significant digits. That's it. For example here, now 0.55 millimeters. How many sig figs? It has a 5 and a 5. That's 2 sig figs. All right, so convert this value to meters, and we get 0.00055. Now, my tool measured 2 significant digits. Just because I mathematically in my calculator convert to meters doesn't mean I should gain any or more or less accuracy. And of course, how many significant digits do I have here? These are not significant. I have still 2 significant digits. There's my line of accuracy. Again, this is to the left, but there's there's no number there. Okay? Anything beyond that point still would be unknown as well. 2 sig figs. These are not significant. They are important. They're just not significant for what we're using them for. Okay, again, 2 sig figs. All right, so convert to micrometers. Now this would be 55,000 micrometers, same value. Again, I have 2 sig figs. I should not have more here. These are trailing zeros. Again, trailing zeros that don't go past the decimal. We treat this as an estimate of 55,000 micrometers. My accuracy line ends still right here, just like it ended right here and right here after the 5. This will be 2 sig figs because trailing zeros are not significant. Trapped zeros. They're in the middle between 2 non-zero numbers. Call them trapped. Trailing, leading, helps you out a little bit what they look like. A trapped zero actually is just like a 0. So this is going to be just like any other number. 1, 2, 3, 3 sig figs. All right, quick practice here. You can pause the video and at this point, and if you want to try them on your own. This guy is going to have, I draw my rounding line on there to show that's an estimate of 250 and would have 2 sig figs. Estimate, not estimate anymore, so 1, 2, 3, 4 sig figs. Past the decimal, so this is not, this 0 does not have to be there. It's there because it was measured. That's going to be 3 sig figs. This one, this one, this one. This is a leading 0. Number hasn't started yet. Leading zeros, they're out. These are good and good. This is past the decimal. They don't have to be there. They're there because the tool measured it. 4 sig figs. That's where my accuracy runs out. Leading zeros, not counted. I have 1, 2, 3, 4, and then these are trailing past the decimal. They are good to go. And there's my accuracy line. 1, 2, 3, 4, 5, 6. 6 zeros. Look at where your number cuts off, and then they're all significant except for the ones that are leading. And there's my numbers. Scientific notation. Okay, this is your base unit and your exponent. Also means this. We will quite often have an E here, which would be represented by times 10 to the 4th. For significant figures, any number that is here is significant. It's been measured by a tool. So converting 5,000 to scientific notation, these zeros are not significant. 5 decimal e to the 3rd. If I want to show a number to be scientific, I can also draw a line over it. So let's say I measured 5,000, and I use a tool to measure all of these guys to actually be zeros. Okay, so 5,000 might actually ends right here. If I were to draw this one as a scientific notation, I would need to include all of these values right here as being significant. 4 sig figs. If I were to transfer this number back, I would include a line over it to indicate that. 1, 2, 3, 4 sig figs. This is no decimal, so it's infinite. This has a decimal, so it's measured at 1 sig fig. Past the decimal, so those are not have to be there. They're actually ends right here. 5. Estimate of 250. Infinite. This one should have a decimal. Meter cannot be measured exactly. So 2 sig figs. There would be a decimal there, but that would be an estimation of 250 meters.